Hello. Today we are going to continue Chapter 8. In the last video on Tuesday, we learned the basic structure of statistical inference. So the idea is that the population is the set of what we want to know, like every every votes for the presidential election. But we cannot observe everyone in the population. So, but instead, we observe just a part of the population, which is the sample. So, statistical inference is to guess, is to infer about the population using the sample. Especially, we are interested in a numerical measure of the population. So we set the target. Usually the target is a numerical measure of the population, and we call that as the parameter of interest. So the parameter of interest is usually mean, probability, variance, median, any kind of measure related to the population. And then we would like to estimate that, or we would like to make some statements about the parameter. But of course, we don't know the parameter. Then we calculate something, a similar measure. The sample counterpart of the parameter is called the statistic. We use statistic to infer about the parameter. And we learned estimation is the easiest way, the most basic method of statistical inference. And we learned a basic two important criteria for an estimator to be good. They are the unbiasedness and the efficiency. So unbiasedness is about the mean of the estimator, and efficiency is about the standard deviation of the estimator. So first, understand that an estimator is random, because if you use a different set of random sample, and if you use the same method to estimate the parameter, still with a different sample, you may get a different value, which is about the randomness, And the randomness is coming from resampling. So when you repeat a random sampling, you are going to have different data set, and even if you use the same method like the sample mean, even if you use the sample average, it will be different if you reselect all the random samples. And then because of that, the estimator is random and it has a distribution. That distribution is the sampling distribution, right? Because the experiment is a random sampling. And based on the sampling distribution, we can calculate the mean and the standard error of the estimator. And simply, the theory can be applied to any estimation problem, but we are particularly interested in the estimation of the population mean. The expectation is our parameter. So even though it's the simplest example, but it's widely applicable. As you are going to see later, the mean can be interpreted in different ways, or many estimators share similar properties to the mean. So we are going to just restrict our focus on estimation of the mean. And one simple result was that the sample average is simply the best estimator for the population mean. So when you are curious about the mean, use the sample mean. That's what we learned on Tuesday. Now, I'm going to start another example, which will motivate a more extended method of estimation. So it's my real experience. When my wife was pregnant, the due date was February 15. Now my son is 4 years old, so it's 2016. And at the time, so of course it's my first. My son is the first baby I had, and I was curious until when can she work? Like, so due date is February 15, but it doesn't mean she can work until February 14th. So there must be uh, some buffer before the due date. And also, I was wondering if I can schedule some appointment on, like, say, February 10th. Is it dangerous if it's important so that I cannot cancel the appointment? Then when is safe and when it's not? So anyhow, these questions are reasonably important and practical questions, and anyone can think about these questions whenever uh, they or their wives are pregnant. Uh, by the way, as you may guess, the due date is not that useful because, as I said, even if the due date is February 15, it doesn't mean February 14 is safe, right? And the probability that my son is actually born on February 15 is very low. There is almost always there will be an error, like even 1 or 2 days. So just like saying February 15, like that information is not enough to me. Of course, if I when I tell my friends about expecting date, that's easy. That's I don't need to give them details. Just say about February 15th. Then oh that's reasonable. When I tell my parents, I say it's about February 15th. But to me, it's not enough. So a better way, if possible, a better way to give me that information about the expecting dates or when the baby will be born is like this. If the doctor could have said this to me, then it would help me a lot. Like the baby will be born between February 5 and February 25. Somewhere in between this interval. However, like doctors, like they're usually I remember the doctor recommended somewhere like buffer around like plus minus 2 weeks around the due date. Anyhow, so using that idea, we may apply this idea to general statistical estimation problem. So far, we have considered point estimation. And literally, it means you are estimating the parameter by a point, by a single number. And it's simple, intuitive, and easy to present and easy to deliver the information, but it's not complete. It does not tell how accurate your estimator is. It does not tell you like how much errors it may have or how much correct, how much accurate it is. So to generalize, to complement that problem, and to provide more information, you may extend a point to an interval. So interval estimation is to estimate a parameter using an interval instead of a point. So point is 1 point and interval is, an interval. And it provides more information, especially about the accuracy of the estimation, right? So let me describe the basic structure of interval estimation. This is actually, it's not a unified framework. In other contexts, the interval estimator could be a little bit different, but it's hard to say every possible cases here. So I'm going to stick to this interval estimator in this course. Especially this is good enough for estimation of the mean. And we are going to, so for interval estimation, the starting point is a point estimation still. So you suppose that you already have a point estimator. We learned what is a good point estimator on Tuesday, so you may refer to that videos and slides if you're curious about what it has to satisfy. Anyhow, suppose that you have a good, reasonable point estimator, theta hat, for a parameter theta. Then this is a point estimator, and what you do here is you are making it as an interval, into an interval. So by adding and subtracting a number to the point estimator. So margin of error is m, and what you do here is you add the margin of error and subtract the margin of error around the point estimator. So this is a notation for an interval. So a square bracket has two numbers with separated by comma, so this is an interval between theta hat minus m and theta hat plus m. And it means that this is an interval estimator, which means that you estimate that the parameter seems to lie between these 2 points. So you believe the parameter is within this interval. And the larger value, the upper end point, is called the upper confidence limit, and the lower point is the lower confidence limit. And the interval itself is called the confidence interval. So I don't know why it's called confidence interval, but I guess it sounds like you are confident that the parameter is lying between these 2 points. This is the structure of interval estimation. And then when you have the confidence interval, now we can think about the probability of correct estimation. So the estimation is correct, the interval estimator is correct if the true parameter lies between theta hat plus minus m. So the theta lies on the interval. So we can think about 2 probabilities. First, the error probability. And error probability is the probability that true parameter is lower than the lower confidence limit, or probability that the true parameter is greater than the upper confidence limit. So it's outside. So interval is here, but if true parameter is here or here, then your estimator is wrong. And in this context, in statistics, this error probability is usually denoted by alpha. Alpha captures the error probability. And its flip side is the probability of correct estimation. 1 minus alpha is the probability that the true parameter lies between the confidence limits, lower confidence limit, upper confidence limit. So this is the probability that the confidence interval contains the true parameter. And we refer to that as the confidence level, how confident you are. If it's 100%, then it's always correct. So we already defined alpha as the error probability. So the confidence level is 1 minus alpha, 1 minus probability of wrong estimation. So this is the basic structure and basic terms and notation, and we are going to develop some basic properties, characteristics of interval estimators in the next video. Thank you.